Hello there, and welcome. I am so glad you found your way here tonight. Come in, settle down, and let whatever weight you have been carrying today just fall away from your shoulders. Maybe it was a long one. Maybe the hours moved too slowly, or far too fast, and your mind is still catching up with everything that happened. The small things, the unfinished things, the things you will deal with tomorrow. That is perfectly fine. You do not have to solve any of it tonight. You have nothing to do tonight but rest. Tonight, we are going to drift very far from home, far beyond the familiar reaches of our solar system, out past the last cold planets, out past the edge of everything we have ever sent a spacecraft to touch, and into the deep, dark ocean of space, where other worlds are quietly turning. These are the exoplanets, worlds orbiting distant suns. Some of them are burning with fire, some are wrapped in eternal night, some are made of things that have no name in any language you have ever heard, and some of them, perhaps, are not so different from the small blue world you are lying on right now. We will not rush. There is nothing to memorize here, nothing to understand perfectly. You are just going to let these worlds wash over you, one by one, like slow waves in the dark. Let your body grow heavy. Let your breathing slow down. And if sleep comes before we are finished, that is not a failure. That is the whole point. If these quiet journeys help you unwind at the end of a long day, consider subscribing, one sleepy soul at a time. Now, let us begin. The Milky Way alone holds an estimated 400 billion planets orbiting other stars. When astronomers first began searching for planets beyond our solar system, they half expected to find a few scattered exceptions, oddities, rarities, cosmic flukes. What they found instead was abundance. Nearly every star in the sky, it turns out, is circled by at least one world. The galaxy is not a mostly empty place, punctuated by rare islands of planets. It is a garden, a slow, silent, impossibly large garden, where worlds grow as naturally as dust gathers in a quiet room. We were not the exception. We were never the exception. We were always just one among billions, resting in the outer arm of a galaxy full of turning, patient worlds. Even now, as you drift, there are 400 billion worlds out there, turning slowly in the dark. The first confirmed exoplanet, orbiting a sun-like star, was discovered in 1995. Before that year, all we had were theories and hope. Astronomers had long suspected that other stars must have planets. The physics seemed to demand it, but no one had ever proved it. Then in October of 1995, two Swiss astronomers, named Michel Mayor and Didier Queloz, announced they had found one. It orbited a star called 51 Pegasi, about 50 light-years away. They called it 51 Pegasi b, and it was nothing like anyone expected. It was a gas giant, enormous and hot, circling its star so closely that a year on its surface lasted only 4 Earth days. It shattered every assumption the field had made, and it opened a door that has never been closed since. That discovery was a small key, turned quietly, that unlocked a universe of worlds. Some exoplanets are so close to their stars that their surface rock melts and rains back down as lava. We call these worlds lava planets, and they exist in a state of permanent, slow catastrophe. The side of the planet facing the star is so hot that rock does not just heat, it vaporizes, rising as vapor into the thin atmosphere, before cooling, condensing, and falling back to the surface as a slow rain of molten stone. The other side of the planet, facing away into space, is cold and dark and still. These worlds spin in locked orbits, one face always burning, one face always frozen, split down the middle into fire and silence. They are extreme in every way, and yet they circle their stars with the same quiet patience as every other world. Somewhere in the dark, a world rains fire and calls it ordinary. Hot Jupiters were the first kind of exoplanet we discovered in large numbers, and they defied everything we thought we understood about planetary formation. A hot Jupiter is exactly what it sounds like. A gas giant the size of Jupiter or larger, but orbiting its parent star at a fraction of the distance Mercury orbits our Sun. They are close enough to their stars that a year lasts only a few days. The heat on their upper atmospheres can exceed 1,000 degrees, and according to the theories we had before we found them, they should not exist where they are. Gas giants are supposed to form far from their stars, where it is cold enough for ice to accumulate. These worlds formed far out, then slowly, over millions of years, migrated inward, drifting toward the heat, dragged by invisible gravitational forces we are still working to fully understand. The galaxy is full of wanderers who ended up somewhere no one expected them to be. The James Webb Space Telescope has begun reading the atmospheres of exoplanets in extraordinary detail. For most of human history, we could only detect exoplanets at all. We could not see them directly, could not touch their light, could not taste their air. But the Webb telescope, launched in 2021 and fully operational by 2022, changed what was possible. By spreading the light of a distant star into its component wavelengths, scientists can identify which chemicals are present in a planet's atmosphere as it passes in front of that star. Water vapor, carbon dioxide, methane, sulfur dioxide. Each molecule absorbs a specific slice of light, leaving a fingerprint we can read from trillions of miles away. We are, in a very real sense, breathing in the air of other worlds, one faint spectrum at a time. Quietly, we are learning to read the breath of worlds we will never visit. There is a planet called WASP-76b, where it rains iron. Not metaphorically, not almost, actual iron, in liquid droplets, falling from the sky on the night side of this world every day. WASP-76b is tidally locked to its star, meaning one side bakes in continuous daylight at temperatures above 2,000 degrees Celsius, hot enough to vaporize iron, which rises into the upper atmosphere and is carried by ferocious winds around to the dark side. On the dark side, the temperature drops enough that the iron vapor cools and condenses into droplets, which then fall. Astronomers detected this process by measuring the iron in the planet's spectrum, and what they found was so strange, it took a moment to believe. A world where the rain is metal, where the sky delivers not water, but iron, falling slowly in the perpetual dark. Somewhere, a night sky is heavy with iron, falling slow and ancient into silence. The majority of exoplanets we have found orbit stars smaller and cooler than our Sun. These are called red dwarf stars, dim, ancient, long-lived suns that burn at a fraction of our Sun's brightness. Because red dwarfs make up about 70% of all stars in the Milky Way, and because many of them host planets, the most common type of world in the galaxy may be one orbiting a star so faint it cannot be seen with the naked eye. From such a planet, the sky would look different. The star overhead would appear larger, but dimmer, a deep orange or red glow, rather than the sharp white light we know. Days would be darker, quieter, colder, and the star itself would live for trillions of years, far outlasting our own Sun. These worlds have time, more time than we can imagine. Ancient light from a dim and patient star, falling on worlds that have all the time in the universe. Astronomers discovered that some exoplanets share a year shorter than a single Earth day. These are the closest-in planets we know of, worlds so tightly bound to their stars that they complete a full orbit in mere hours. One of them, called KOI-1843.03, orbits its star every 4.5 hours. Its surface is almost certainly molten. Its sky is dominated by the enormous face of its star, filling the horizon like a wall of fire. Gravity on the surface of such a planet would be relentless, crushing. And yet the planet holds together. The same gravity that keeps it locked in orbit also keeps it from being pulled apart. It is a world living right at the edge of what is possible, circling in tight, breathless loops, patient in its own violent way. Even at the edge of destruction, the orbit holds. Everything finds its own quiet rhythm. There is a class of worlds called ocean planets, exoplanets, where the entire surface may be covered in a deep, global ocean, with no land, no shore, no beach. Just water, all the way to the horizon in every direction, down to depths we cannot calculate. Earth has oceans, but they are shallow by comparison, a thin film on the surface of a mostly rocky world. An ocean planet would be water all the way down for hundreds of miles before reaching any solid interior. The pressure at those depths would be so extreme that water would not remain liquid. It would compress into a form called high-pressure ice that exists nowhere on Earth. A strange, dense, silent layer of solid water at the heart of a world made entirely of sea. Rest in the thought of that, a world of nothing but still, deep, ancient water, all the way down. As you rest tonight, consider that more new exoplanets are confirmed every single week. The count passed 5,000 confirmed exoplanets in March of 2022, and it has been climbing steadily ever since. Each one is a data point in a growing picture of the universe's variety. Some are discovered by the transit method, watching for a planet to pass in front of its star and briefly dim the starlight. Some are found by the radial velocity method, detecting the tiny gravitational wobble a planet causes in its star's motion. A few have been directly imaged, tiny dots of light beside the bright glare of their suns. Every method reveals different kinds of worlds, different sizes, different distances, different temperatures. We are building a catalog of worlds, slowly, one at a time, in the quiet dark. A quiet catalog of distant worlds, growing longer every week, in every direction. Super-Earths are perhaps the most common type of planet in the galaxy, yet we have none in our own solar system. A super-Earth is simply a rocky planet larger than Earth, but smaller than Neptune, a category that sits between the familiar and the enormous. They can be anywhere from 1.5 to 10 times Earth's mass. They might have thick, dense atmospheres. They might have deep oceans. They might be rocky deserts or covered in exotic minerals we have never encountered. What makes them remarkable is their absence here. Our solar system skipped this category entirely, jumping from small rocky worlds like Earth and Mars to giant ice planets like Uranus and Neptune. The most popular type of world in the galaxy is one our own system never made. We live in a solar system that never built the most common kind of world. Quietly, that is worth sitting with. Some exoplanets have 2 suns, and watching a double sunset from their surface would be a slow, golden, dreamlike thing. Circumbinary planets, as they are called, orbit 2 stars that themselves orbit each other. The planet KEG 16b, discovered in 2011, was the first confirmed circumbinary world, immortalized in popular culture as the inspiration for the twin sunset scene in a certain famous space story. From the surface of such a world, you would watch one star set, then the other, or sometimes both at once, depending on where in the orbit you stood. The light would shift from white to orange to gold as each sun descended. Night, on a circumbinary world, might be brief, or very long, or nearly non-existent, depending on how the 2 stars align on any given day. 2 suns setting, one after the other, painting the sky twice with the same slow gold. The planet HD 19733b appears to be a deep, vivid shade of blue. But that blue is not ocean, it is glass. This world, one of the best studied exoplanets we know, is a hot Jupiter orbiting very close to its star. Its atmosphere is laced with silicate particles, tiny, sharp shards of mineral suspended in the high atmosphere. These particles scatter blue wavelengths of light in the same way Earth's atmosphere scatters sunlight, giving the planet its striking color when imaged directly. But the wind on HD 189733b reaches speeds of 5,000 miles per hour. Those silicate particles are not drifting. They are screaming through the atmosphere sideways, in a perpetual, silent from a distant storm. It is the most beautiful and most violent thing in the neighborhood. A blue world, seen from afar, looks like calm. Up close, it is always something else. There are rogue planets drifting through the galaxy with no star at all. They were once part of solar systems, worlds formed around a sun, circling in an orbit, and then, through some collision or gravitational interaction, they were flung free. They now travel through interstellar space in total darkness, with no star to warm them, no light to illuminate their surfaces. The universe may contain more rogue planets than there are stars. They are the quiet wanderers of the cosmos, untethered, unhurried, invisible. Some of them may still retain enough internal heat from their formation to maintain liquid water beneath a frozen surface. Life, perhaps, traveling between stars on a dark and patient world, with no sun and no shore, drifting through the long night between galaxies. A world with no star drifts in patient darkness, carrying whatever it carries, going wherever it goes. The atmosphere of an exoplanet can be stripped away by its star. This process is called photoevaporation, and it is slow, relentless, and total. When a planet orbits very close to its host star, the intense radiation and particle wind from the star gradually erodes the upper layers of the planet's atmosphere. Over millions and billions of years, entire atmospheres can be lost this way. A planet that was once a small gas world is gradually sculpted down to its rocky core, the atmosphere blown away into space, like fog before a wind. We have found what appear to be the bare cores of stripped planets, called sub-Neptunes, or super-Earths, and they may be what was left behind when the gas was gone. Quiet, bare, rocky remnants of worlds that were once something else entirely. Slowly, patiently, the star takes back what once surrounded it. Everything returns, in time. There is an exoplanet whose year lasts only 18 hours. It is called Kepler 78b, and it is one of the most extreme worlds in our catalog. It orbits its star at a distance of less than twice the star's own diameter, meaning if you stood on its surface, the star would fill most of your sky, a burning wall so close it seems impossible the planet has not been swallowed entirely. And in fact, the tidal forces between the planet and its star are slowly pulling the planet inward. Over millions of years, Kepler 78b will spiral closer and closer until it is absorbed by the star itself. It is living on borrowed time, but for now, it circles, patient and oblivious, completing a full year in the time it takes you to sleep and wake and go through a day. A world circling its star in less than one day, unaware that it is slowly falling home. Kepler 22b was one of the first exoplanets discovered in the so-called habitable zone of its star, the region where liquid water might exist on a planet's surface. Its star is slightly smaller and cooler than our Sun, and Kepler 22b sits at just the right distance that temperatures might allow water to pool and stay liquid. We do not know yet if it has water. We do not know if it has an atmosphere, or what that atmosphere might be made of. We do not know if it is rocky, or a deep ocean world, or something else entirely. But it sits in the right place. It is the right distance from the right kind of star. It is the first in a long list of worlds where the conditions are at least not impossible for life as we know it. A world in the right place, with all the right distances, quietly waiting for us to learn its name. The technique of gravitational microlensing has revealed exoplanets thousands of light years away. Most planet-finding methods work best on nearby stars, close enough for the instruments to detect the subtle signals. But microlensing works across enormous distances. When a foreground star passes in front of a background star, as seen from Earth, the foreground star's gravity bends and magnifies the background star's light like a lens. If the foreground star has a planet, that planet creates a secondary, brief brightening in the light curve, a tiny signal that lasts only hours or days, never to repeat. It is a one-time event. A single window. We watch it happen, collect the data, and the planet is gone, known to us only by the ghost of light it left in our instruments as it passed through the dark. A ghost of light, briefly bent, and a world revealed, then gone, drifting on in silence. Some exoplanets may have moons, and those moons might be more habitable than the planets themselves. Just as our own moon orbits Earth, large exoplanets could host moons of significant size. A moon, orbiting a gas giant in the habitable zone of its star, would have a complex, beautiful sky, the enormous face of the planet overhead, the star a bright point further out, other moons tracing slow arcs across the night. The gravitational interaction between the planet and the moon could generate internal heat, keeping the moon warm, even when the star's light alone would not be enough. Some scientists believe that when we finally find extraterrestrial life, it may not be on a planet at all. It may be on a moon, quiet and warm, and tucked under the arm of a much larger world. Life, perhaps, sheltered beneath the vast, slow curve of a gas giant's shadow, dimly lit, quietly orbiting, patient. The exoplanet Proxima Centauri b is our nearest known neighbor. It orbits Proxima Centauri, the closest star to our Sun, at just 4.2 light-years away. That is still 25 trillion miles, a distance so large that even the fastest spacecraft we have ever built would take tens of thousands of years to reach it. But by cosmic standards, it is our backyard. Proxima Centauri b sits within the habitable zone of its star. It may be rocky, it may have an atmosphere, and because Proxima Centauri is a red dwarf, it bathes its planet in a different quality of light, dim, reddish, and occasionally violent, since red dwarfs can flare with intense bursts of radiation. Whether life could survive on Proxima b remains one of the most quietly urgent questions in science. Our nearest neighbor, just 4 years of light away, resting quietly in the dark, and we still do not know what it is. The transit method of finding exoplanets watches for the faintest possible dimming of starlight. When a planet passes between its star and our telescopes, it blocks a tiny fraction of the star's light. For a planet the size of Jupiter, this dimming is about 1%. For an Earth-sized planet, it is closer to 1/100th of 1%, a change so small it was nearly impossible to detect until we put telescopes in space, above the blurring effects of Earth's atmosphere. The Kepler Space Telescope, launched in 2009, stared at a single patch of the sky for 4 years without blinking, watching the brightness of more than 150,000 stars simultaneously, waiting for the faint, repeated dips in light that signal a world in orbit. It found thousands. Patient watching, rewarded by patient skies. The stars flickered, barely, and we learned to read what the dark was hiding. TRAPPIST-1 is a small, dim star, 40 light-years away, that holds 7 rocky planets, and 3 of them sit within the habitable zone. 7 worlds, orbiting a single red dwarf, so small it is barely larger than Jupiter. They circle so close to their star that all 7 planets could fit within the orbit of Mercury around our Sun. A year on TRAPPIST-1b, the innermost, lasts less than 2 Earth days. A year on TRAPPIST-1g, the outermost of the 7, lasts about 19 Earth days. If you could stand on one TRAPPIST planet and look up, you would see the other planets as bright disks in the sky, not just points of light, but worlds, visibly round, moving slowly against the stars. A solar system where the planets are neighbors you could almost wave to. 7 worlds, each one a dim disk in the other's sky, circling in quiet proximity. The radial velocity method detects planets by the wobble they create in their star. Every planet exerts a gravitational pull on its star, not just the star on the planet. A massive planet like Jupiter causes its star to wobble back and forth by a small but measurable amount. This wobble creates a Doppler shift in the star's light. The star appears to move slightly toward us, and then slightly away, which changes the frequency of its light in ways our instruments can detect. For our Sun, Jupiter causes a wobble of about 12 meters per second, about jogging speed. An Earth-mass planet would cause a wobble of less than 1 meter per second, barely a gentle walking pace. We are listening to the stars sway, very slightly, pulled by the invisible grip of their orbiting worlds. A star moves, barely, swaying in the gravity of a world too small to see. We feel it anyway. The planet GJ1132b may have had its original hydrogen atmosphere stripped away and replaced by a new one. This world, orbiting a red dwarf about 41 light-years away, was detected by the Hubble Space Telescope to have a thin atmosphere. Unexpected, because its star should have long ago stripped any original atmosphere clean away. The current thinking is that the atmosphere being observed is a secondary one, outgassed from the planet's interior. Volcanic activity releasing gases from deep within the rock, slowly refilling the space around the planet after the original atmosphere was lost. A planet that lost everything, and then quietly, patiently, rebuilt itself from the inside. It is a form of resilience, so slow, it can only be called geological. Even a world that lost its atmosphere can breathe again, slowly, from the inside out. Some exoplanets exist in binary star systems, where the two stars are so close together they are nearly touching. These are called contact binaries, systems where two stars share an outer layer of gas, pressed together by mutual gravity into a figure-8 shape. A planet orbiting such a system would have a sky unlike anything we can imagine. Two stars, so close, they blur into one elongated, dim shape at the center of the sky, pulsing slightly as they rotate around each other, pulling each other in a slow, inevitable embrace. Astronomers believe contact binaries eventually merge into a single larger star. A planet that survives around such a system would watch, over millions of years, as its two suns slowly became one. The sky changing so slowly, no creature could ever witness the full arc of the transformation. Two suns pulling toward each other, over millions of years, in a slow and patient embrace. The night side of a tidally locked exoplanet may be one of the most profoundly dark places in the universe. Tidal locking happens when a planet's rotation rate slows until it exactly matches its orbital period, so one side of the planet always faces the star, and the other side always faces away into space. The dark side receives no direct starlight, ever. For a planet close to its star, the dark side can reach temperatures of -150 degrees Celsius or colder. But winds from the hot day side carry some heat around the limb of the planet, creating strange weather patterns. Enormous storms, jet streams of unimaginable speed, thin atmospheres that freeze and thaw at the border between day and night. The dark side is cold, windswept, and perpetually facing the open void. On the far side of a distant world, the dark is deeper and more patient than any dark we know. Tonight, while you breathe slowly, consider this. Astronomers estimate there may be 40 billion Earth-sized planets in the habitable zones of sun-like and red dwarf stars in our galaxy alone. 40 billion. That number is not a guess. It is a calculated estimate based on the rate at which Kepler found such planets within the small patch of sky it watched. Extrapolated across the full Milky Way, the number of potentially habitable worlds is staggering. And the Milky Way is only one of an estimated 2 trillion galaxies in the observable universe. We may be unique, we may be rare, but the universe has had an enormous amount of time and an unimaginable amount of space in which to try. And it does not appear to have been wasteful. 40 billion chances at something like home, scattered like quiet lights across the dark. The exoplanet 55 Cancri E may be covered in a global ocean of supercritical carbon dioxide. This is not ocean in any way you might picture it. Supercritical CO2 is a state of matter that forms under extreme pressure and temperature, where the substance is neither quite liquid nor quite gas. It flows, but densely, with properties of both. The surface temperature of 55 Cancri E is estimated at around 2000 degrees Celsius. Any ocean on its surface would be a churning, dense fluid of exotic chemistry. Nothing like water, nothing like anything Earth has ever had on its surface. And yet the word ocean still applies. a world covered in fluid, a slow, dense, scalding sea of carbon, with no shore, no wave, no tide, just the steady, pressured flow of a hot and ancient chemistry. A scalding ocean with no shore, no wave, no tide, just heat and pressure and patience. Cold gas giants that sit far from their stars are sometimes called failed Jupiters, worlds that began the process of becoming brown dwarfs, but never gathered quite enough mass. A brown dwarf is sometimes called a failed star, an object massive enough to begin some nuclear reactions, but not enough to sustain them. A cold gas giant is one step below even that. It formed in the outer cold of a solar system, gathered gas and ice, swelled large, and then simply stopped. It does not glow. It does not shine. It orbits in the dark and the cold, giving off a faint infrared warmth from the heat of its formation, slowly cooling over billions of years. In the very far future, billions of years from now, all gas giants will eventually cool to near absolute zero and go completely dark, patient, cold, and still. Even the giants, given enough time, go quiet and cold and drift in the dark. The atmospheres of gas giant exoplanets can host clouds made of minerals and metals rather than water vapor. On Earth, clouds are made of water, droplets of liquid or crystals of ice suspended in the air. But on a hot Jupiter, the atmosphere is so hot that the clouds condense from entirely different materials: iron clouds, magnesium sulfide clouds, titanium oxide haze. These mineral clouds form in the cooler upper layers of the atmosphere, where the temperature drops enough for the metal vapors to solidify into tiny particles. A hot Jupiter viewed from space might show the same swirling cloud patterns as a gas giant in our solar system. Beautiful bands and storms and curving jet streams, but those clouds would be made of metal and mineral dust, drifting in the high winds of a world where it is too hot for water to exist. High above a world too hot for rain, clouds of iron drift slowly in the ancient dark. Kepler 186f was the first Earth-sized planet discovered in the habitable zone of another star. Found in 2014, it orbits a small red dwarf, about 500 light-years away. It is roughly the same size as Earth, one of the most similar to our world in raw size that we had found up to that point. Its star is cooler and dimmer than our Sun, so even though Kepler 186f receives less light per unit of surface area, the reduced distance to its star keeps temperatures within a possible range. Standing on its surface, if it has a solid surface, you would feel a gravity similar to Earth's. The sky might be darker, the sunlight redder and dimmer, but there would be a sky, there would be a surface, there would be a world. 500 light-years away, an Earth-sized world quietly exists, and we know its name. 500 years of light between us, and still we found it, dim and patient in the dark. Some exoplanets have been found in what is called a resonance chain, a gravitational arrangement where each planet's year is a simple multiple of its neighbor's year. In the TRAPPIST-1 system, the planets orbit in a resonance pattern so precise it resembles a musical rhythm. If you assigned each planet a note and played them based on their orbital period, you would hear something approaching a slow, complex chord, the inner planets completing 2 or 3 orbits for every 1 orbit of the outer planets, all locked together in a gravitational harmony that has been stable for billions of years. It is not random. It is the result of billions of years of slow, patient gravitational tuning, as the planets migrated and settled into the positions that kept them all safe. 7 worlds in a slow and ancient chord, resting in a harmony they did not choose. Some exoplanets are so massive and so dense that they are called super-dense Earths, worlds where the surface gravity would be 5 to 10 times stronger than what we feel here. On such a world, the atmosphere would be thick and crushing, pressed down by gravity so strong that the air itself would feel like water. Moving through it would require enormous effort. Rain, if it fell, would fall faster and harder. Even standing upright would be difficult. Every gram of matter on such a world is pulled more firmly toward the center. Mountains would be lower, pressed flat by gravity over geological time. The oceans, if any existed, would be shallower and denser. These worlds are not hostile in the way a lava planet is hostile. They are simply heavy, heavier than anything we have stood on, quietly pressing everything down. Some worlds hold everything more tightly than ours does, pressing all of it gently but firmly into place. The exoplanet HAT P7b experiences winds so powerful that they may drive sapphire and ruby clouds across its night side. This world is a hot Jupiter in a very tight orbit, with temperatures on its day side exceeding 2,000 degrees Celsius. The atmosphere includes aluminum oxide, the same compound that forms rubies and sapphires, and on the cooler night side, this material condenses into tiny crystalline particles. The winds on HAT P7b are so fast and so powerful that they intermittently shift direction, making the distribution of these gem-like clouds unstable and dynamic. Huge banks of crystalline haze, made of material that on Earth becomes precious stones, blowing back and forth across the permanent night of a world that has never known stillness. Clouds of ruby and sapphire, blown through the dark, cold, and patient, and quietly beautiful. Even now, as you drift, consider how the universe builds things of beauty in the places most hostile to life. There is a planet called WASP 189b that orbits one of the hottest stars known to host a planet, a star so massive and bright that most stars of its type are not expected to maintain a stable planetary system. And yet WASP 189b orbits there, a gas giant in tight orbit around a blue star, receiving 30,000 times more radiation per unit area than Earth receives from the Sun. Its temperature exceeds 3,000 degrees. It emits its own light, visible even against the glare of its host star. It is not just illuminated, it glows on its own, a world so hot it has become a dim star itself. A world and a star, pressed so close together, they have begun to blur the line between one kind of thing and another. At the edge of a blue and ancient sun, a world grows bright enough to glow, quietly, on its own. The discovery of dimethyl sulfide in the atmosphere of K218b sent careful ripples through the scientific community. Dimethyl sulfide is a molecule produced on Earth almost exclusively by living organisms, specifically marine phytoplankton. If it were confirmed in the atmosphere of K218b, a world about 8.5 times Earth's mass, orbiting a red dwarf about 120 light-years away, it would be a serious candidate for a biosignature, a chemical that life, and only life, is known to produce. The detection in 2023 was preliminary, flagged as requiring further observation. Scientists were careful, measured in their language. They did not claim life. They said, "We see something worth looking at more carefully." That is how science moves. Slowly, quietly, checking twice before it speaks. The universe offers a faint signal, and we lean in, quietly, careful not to mistake hope for evidence. Circumbinary planets in widely separated binary systems can have remarkably stable orbits over billions of years. When two stars orbit each other at very large distances, thousands of astronomical units apart, a planet orbiting just one of them can maintain a stable orbit for an extraordinarily long time. The gravitational influence of the distant companion star is too remote to perturb the orbit significantly. These planets inherit a kind of solitude. Their star's companion is so far away that it appears only as a bright star in the night sky, not a second sun overhead. The world's seasons and climate are shaped entirely by the single star it orbits, while the distant companion watches from afar, a bright and patient light that never sets. A distant star watches from across the system, too far to influence, too present to ignore. Some exoplanets have magnetic fields strong enough to protect their atmospheres from stellar radiation. On Earth, our magnetic field is generated by the motion of liquid iron in our outer core, a slow, deep dynamo that deflects the solar wind and keeps our atmosphere from being stripped into space. Mars once had a magnetic field and then lost it, and the solar wind gradually eroded its thick atmosphere into the thin wisp we see today. Some exoplanets, particularly large rocky ones, may have active magnetic fields that protect their atmospheres in the same way Earth's does. These fields are invisible, but they are barriers, the difference between a world that keeps its air and one that slowly loses it to the patient erosion of its star's wind. Invisible, unfelt, and silent, the magnetic field holds the air in place, and the world breathes on. White dwarf stars, the collapsed remnants of dead sun-like stars, have been found with rocky debris orbiting them, and sometimes with surviving planets. When a sun-like star exhausts its fuel, it swells into a red giant and then sheds its outer layers, leaving behind a dense white dwarf about the size of Earth, but with the mass of a star. Any close-in planets are consumed during the red giant phase, but planets in wide, distant orbits can survive, and the rocky debris that orbits some white dwarfs appears to come from planets or asteroids that were disrupted and pulled apart, their material drifting in slow rings around the dead star's core. These are the graveyards of solar systems, the quiet aftermath of a star's long life, strewn with the remains of the worlds that could not last. Even after a star dies, something remains circling it, patient, slow, and cold in the long dark. The presence of phosphine gas in a planet's atmosphere could be a sign of life, and its detection is extraordinarily difficult. Phosphine is a molecule made of phosphorus and hydrogen. On Earth, it is produced in certain low-oxygen environments and by certain microbes. It is almost impossible to produce in large quantities through purely geological or chemical processes. If detected in the atmosphere of a rocky world in the habitable zone, it would be one of the strongest possible hints that something biological might be happening. Searches for phosphine in exoplanet atmospheres are at the very edge of what current telescopes can do. We are listening for a faint chemical whisper across light years of space, in the air of a world we have never visited, for a signal we have never received before. We are listening, quietly, for a whisper from the chemistry of a distant living world. The exoplanet Gliese 667cc orbits a star that is itself part of a triple star system. To stand on its surface would be to look up at a sky containing, potentially, 3 different suns at various stages of setting and rising. The primary star, Gliese 667c, is a red dwarf, and Gliese 667cc sits in its habitable zone. But the system also contains 2 other stars, Gliese 6667a and b, which orbit each other at a closer distance, and then orbit the C component at a much wider separation. From the surface of Gliese 667cc, those 2 distant stars would appear as bright points of light, much brighter than our brightest stars appear from Earth, but not bright enough to cast shadows. Twilight on this world might come with 3 separate light sources fading at different rates, the sky dimming in layers, slowly. 3 suns setting in sequence, the sky going dark in slow, unhurried layers, one light at a time. Exoplanets in the galactic center orbit in environments far more crowded and violent than anything in our quiet corner of the Milky Way. Near the center of the galaxy, stars are packed much more densely. Instead of the 4 light years between our sun and the nearest star, central stars might be separated by a fraction of a light year. Radiation levels are higher. Gravitational interactions between nearby stars are more frequent. Supernovae occur more often in the denser stellar populations near the core. A planet in this region would be bathed in more radiation, subject to more gravitational tugging from passing stars, and potentially disrupted more frequently. Whether life could arise in such an environment is unknown, but planets exist there, circling in the crowded, bright, restless center of the galaxy, while we rest here, far out in the quiet suburbs. We live in the calm outskirts of the galaxy, far from the restless, crowded center. Some exoplanets may be slowly evaporating before our instruments, their atmospheres streaming away into space like the tail of a comet. For planets that orbit very close to bright, hot stars, the radiation pressure and particle wind can literally blow the upper atmosphere outward into a visible tail. Using spectroscopy, astronomers have detected hydrogen and helium streaming away from certain hot Jupiters at extraordinary rates. One planet, GJ3470b, is losing its atmosphere so quickly that it will be substantially different in size within a billion years. What was once a Neptune-sized world will become something closer to a bare rock. We are watching, in real time, in geological terms, a planet being unmade, the star, patiently, slowly, without any awareness of what it is doing, taking back what it gave. The star takes back the atmosphere it once allowed, slowly, without knowing or stopping. The universe is patient, so are we. Some stars hold their planets in orbits so stable they have remained unchanged for billions of years. Not every solar system is chaotic. Not every planet migrates. Some worlds settle into their orbits early and stay there, locked into the same elliptical path, circling their star with the same quiet regularity for a span of time that dwarfs anything in human experience. Our own solar system has been relatively stable for the past 4 billion years, and some exoplanet systems appear even more so. Stability in the universe is not guaranteed. It is earned, slowly, through the gradual dissipation of the chaos that comes with formation. What remains when the chaos settles is a system in balance, planets in their lanes, moons in their orbits, everything turning together in the long and patient dark. Stability, once found, is kept not by effort, but by the slow forgetting of former chaos. There are planets made almost entirely of carbon, worlds where the geology is built from graphite and diamond, rather than silicate rock and iron. On Earth, the mantle is made of oxygen-rich silicates. But if a planet forms from a disk of material, where carbon is more abundant than oxygen, the chemistry of the entire world changes. The crust might be graphite. Deep in the interior, under the enormous pressure of the overlying rock, carbon would crystallize into diamond. A planet with a diamond mantle, not glittering and clear like a gem. Diamond at those pressures and temperatures behaves more like a dense, dark mineral, but made of the same carbon lattice as the stones we prize. Entire worlds built from the element at the heart of all life on Earth. Vast, silent, dark, and made of something we spend centuries mining grain by grain from the crust of our own small world. Deep beneath the surface of a carbon world, the dark is made of diamond, patient and immovable. Water worlds may have oceans hundreds of miles deep, covering whatever rock lies beneath, in a blanket of silent fluid. We have ocean floor on Earth at about 7 miles below the surface, the deepest point in the Mariana Trench. But on a water world with 10 times the water fraction of Earth, the pressure at the base of the ocean would be so enormous that water itself changes phase. It would become what scientists call Ice 7, a form of high-pressure ice that exists even at very high temperatures, solid not because it is cold, but because it is squeezed so tightly that its molecules cannot flow freely. Beneath the ocean of a water world, there is no seafloor of mud and rock. There is only dense, strange ice pressing down into the planet's interior. The ocean just keeps going, changing form but never ending. An ocean with no bottom, except the slow transition into something harder and more still. The brightness of a star, as seen from its planet, determines everything about that world's experience of light. From Proxima Centauri b, the nearest known exoplanet, the host star would appear much larger in the sky than our sun appears to us, but far dimmer overall, a deep orange-red glow rather than the sharp white disk we know. The quality of light falling on a world shapes what colors plants can use for photosynthesis, what wavelengths warm the surface, what kinds of shadows form. Life on a world orbiting a red dwarf might have evolved to use different pigments to capture the dimmer, redder light. Black or deep purple leaves, instead of green, absorbing every photon the weak sun offers. A forest that looks, from the outside, like a shadow. A forest of dark leaves, quietly drinking whatever faint and ancient light its star provides. Some exoplanets have been found to have dramatically eccentric orbits, not the nearly circular paths of our own planets, but elongated ellipses that take them very close to their star and then very far away, over the course of a single year. Imagine a world whose seasons are not caused by axial tilt, but by raw distance from its sun. In the closest part of the orbit, the star fills the sky, and the surface scorches. In the farthest part, the star shrinks to a bright point, and the temperature plummets. A single year on such a world is a journey from fire to ice and back again, a dramatic, extreme swing that no life as we know it could easily survive. And yet the planet itself endures it, year after year, patient and indifferent to its own extremity. A world that passes through fire and ice every year, quietly enduring both. As you rest tonight, the Kepler Space Telescope's archive continues to yield new exoplanet candidates, long after the telescope itself went silent. Kepler ran out of fuel and was retired in October 2018, but the data it collected during its 9 years of operation is still being analyzed. Scientists and even citizen volunteers using distributed computing projects continue to sift through the light curves of hundreds of thousands of stars, looking for the faint signatures of transiting planets that were missed in initial processing. New exoplanets are being found in old data, worlds that were always there, hidden in the numbers, waiting for someone to look at the right column of numbers at the right time. The telescope is gone, but the knowledge it gathered is still arriving, quietly, years after it went dark. A silent telescope, years retired, still giving up its secrets slowly in the dark. There is a region around every star called the frost line, and where a planet forms relative to this boundary shapes everything about what kind of world it becomes. The frost line is the distance from a star at which it becomes cold enough for water ice and various other volatile compounds to condense into solid form in the protoplanetary disk. Planets that form inside the frost line are rocky. The ices evaporate and blow away, leaving only the dense, refractory materials to accrete. Planets that form outside the frost line incorporate ice into their structure from the beginning, growing larger, incorporating more mass, often becoming gas giants. The frost line is an invisible threshold, no visible marker in space, but it is one of the most consequential boundaries in the life of a planetary system, deciding from the very beginning whether a world will be rock or gas, small or vast, solid or wrapped in 1,000 miles of cloud. An invisible line in space, crossed at formation, that decides everything a world will ever be. Some exoplanets have been found inside the debris disks, left over from their star's formation, rings of dust and planetesimals that have not yet fully coalesced into larger bodies. From the surface of such a planet, the night sky would be filled not with the deep black emptiness between stars, but with a faint, glowing band of scattered light. The disk itself, reflecting the starlight back. It would look, perhaps, like a permanent aurora, a soft, diffuse glow wrapping the sky in a constant dim light, never quite dark enough for true night. The planet would be surrounded by the raw material of other worlds not yet made, dust and ice and rock, still deciding whether to fall inward or drift apart, suspended in the patient, ongoing process of formation. A world surrounded by the dust of worlds not yet made, resting inside a still-forming sky. The exoplanet Tau Boötis b may be losing its atmosphere so fast that it is essentially painting a comet-like tail of gas behind it as it orbits. Atmospheric escape from hot Jupiters has been known for some time, but in some cases, the loss rate is dramatic enough to produce a detectable extended atmosphere, a cloud of escaping gas that trails the planet in its orbit, sometimes wrapping partway around the star. These extended atmospheres make the planet slightly easier to detect and study, because the larger apparent size of the escaping gas cloud creates a more pronounced dimming when it transits. In a way, the planet advertises its own slow destruction, a world trailing its own dissolution behind it like smoke, still circling faithfully, even as it diminishes. Quietly, a world trails the cloud of its own slow ending, like smoke behind a drifting flame. Even now, as you drift, enormous gas giants in distant solar systems are quietly shepherding asteroid belts and protecting their inner planets from impacts. In our own solar system, Jupiter's immense gravity acts as a gravitational vacuum of sorts, capturing or deflecting a large fraction of the comets and asteroids that would otherwise strike the inner planets. This may have played a role in allowing life on Earth to develop without constant catastrophic bombardment. In exoplanet systems, astronomers look for whether gas giants exist in the right orbits to perform this same protective function. A solar system without a Jupiter equivalent in the right place might suffer more frequent large impacts, resetting any developing life repeatedly. The giants, quiet and distant, protect the small by simply being there. The largest worlds, circling far out in the cold, protect the small ones without knowing it. Some exoplanets have cloud layers at multiple different altitudes, each made of a different substance, creating layered weather systems of extraordinary complexity. On Earth, clouds are all made of water in different phases, but they form at different altitudes and produce different kinds of weather. On a hot Jupiter, this layering becomes extreme. Deep in the atmosphere, iron and silicate clouds. Higher up, perhaps magnesium sulfide. Higher still, sodium and potassium vapor. Each layer has its own temperature, its own wind speed, its own chemistry. Weather on such a world would be a vertical journey through different chemical environments, each with its own kind of precipitation, its own kind of darkness. From below, looking up, the sky would be a ceiling of cloud above cloud above cloud, each layer drifting at a different speed, layer upon layer of cloud, each made of something different, drifting above and below each other in quiet procession. The shortest possible orbit for a planet without being torn apart is called the Roche limit. Inside this distance, the tidal forces from the star exceed the gravitational self-cohesion of the planet, and it would be pulled apart, shredded into a ring of debris, just as moons have been torn apart to create Saturn's rings. Most planets we observe outside this boundary are under no immediate threat, but some of the closest in exoplanets we know orbit uncomfortably near it. Not inside, but near enough that the distinction feels fragile. These worlds circle their stars at the edge of their own integrity, held together by exactly enough gravity to remain a planet, with the tidal forces of their star pressing outward at every surface. They are intact, but barely, and quietly, they endure. Held together at the very edge of being torn apart, the world circles on, patient and whole. Planets in binary star systems can orbit just one star, or they can orbit both stars at once. The ones that orbit just one star are called S-type planets, and those that orbit both are called P-type or circumbinary planets. S-type planets need to orbit closely enough to their host star that the gravitational influence of the distant companion does not destabilize their path, typically staying within about 1/5 of the distance between the two stars. P-type planets, on the other hand, must orbit far enough out from both stars that their orbit is not chaotic, typically outside about 3 to 5 times the binary separation. Between these two safe zones, there is a region where stable planetary orbits simply cannot exist. A gap in the architecture of possible worlds, maintained by the mathematics of gravitational tug-of-war, silent and invisible and absolute. Between two stars, a space where no stable world can rest, held empty by mathematics alone. The radio emissions from certain exoplanets may one day allow us to detect their magnetic fields from light years away. Charged particles from a star, when they interact with a planet's magnetic field, can generate radio waves, just as Jupiter emits radio waves from its own strong magnetosphere. If a rocky exoplanet has a strong enough magnetic field, and if its star is active enough to produce a strong particle wind, the interaction might produce a radio signal detectable across interstellar distances. This would allow us not just to find the planet, but to characterize it, to say, from here, that a world exists there, and it has a magnetic field, and that magnetic field is currently interacting with the wind of its star, a planet announcing its invisible shield across light years of space. A world we cannot see broadcasting, silently, the presence of its invisible shield. The color of an exoplanet's star determines the color of the sky on any worlds it hosts. Our sky is blue because our sun emits a broad spectrum of light, and Earth's atmosphere scatters shorter wavelengths, the blues, more effectively than longer ones. Around a red dwarf, the incoming light would be heavily weighted toward red and infrared. The sky might be orange, or a deep, low salmon color, or even a dusty brownish hue depending on the atmospheric composition. Around a hotter, blue-white star, the sky could be a different shade entirely, more violet, or a pale, washed-out silver blue. Every world carries its star's color signature in its sky. The quality of light shapes the color of everything that grows, everything that sees, everything that looks up. The color of a world's sky is a gift from its star, passed quietly through every layer of air. Quietly, the universe holds planets that orbit dead stars, remnants of solar systems that survived the death of their sun. When a massive star ends its life in a supernova, the explosion can scatter the protoplanetary disk and destroy any nearby worlds. But the first exoplanets ever discovered, before any planet around a sun-like star, were found orbiting a pulsar, the dense, rapidly spinning remnant of a dead star. These are called pulsar planets, and they are among the strangest objects known. They orbit a star that pulses with intense radiation, completing their orbits in a fierce, battering radiation field, exposed to energies that would strip any atmosphere in moments. They likely formed after the supernova from the debris of the explosion itself. Second-generation planets, born from destruction. From the ashes of a dead star, new worlds formed, patient, quiet, and strange. Even now, as you drift, there are stars being born somewhere in the Milky Way, surrounded by protoplanetary disks that will one day become solar systems. Star formation happens continuously in our galaxy, in regions called stellar nurseries, vast clouds of gas and dust that have collapsed under their own gravity, sparking new stars at their centers. Around each newborn star, the remaining gas and dust settles into a rotating disk. Within that disk, particles collide and stick together, growing from dust grains to pebbles to planetesimals to planets. The whole process takes a few tens of millions of years, which sounds long, but is less than 1% of the age of the universe. New worlds are forming right now, in this same galaxy, in this same night. Somewhere in the dark, tonight, a new world is quietly taking shape around a newborn star. Some exoplanets have surfaces that are entirely covered in a single mineral, depending on how they formed and how their geology evolved. A world rich in sulfur might be yellow, its plains and mountains all composed of the same pale, waxy mineral. A world of iron oxide would be red, like Mars, but more so, a deeper and more uniform rust. A world of magnesium silicate might be pale gray, its surface resembling nothing so much as the inside of an enormous cave. These are not hypothetical. The minerals exist. The chemistry of planetary formation can produce them, and in systems with unusual elemental abundances, such worlds may be common. They are monochromatic in the most literal sense. One color, one material, one geology, all the way to the horizon. A world of a single color, uniform and quiet, stretching unchanged to every horizon. The idea of a habitable zone has expanded in recent years, to include subsurface oceans on worlds that appear, from the surface, entirely frozen. Europa, a moon of Jupiter, is covered in ice, but beneath that ice, kept liquid by tidal heating from Jupiter's gravity, lies a saltwater ocean, larger than all of Earth's oceans combined. Similar conditions may exist on exoplanet moons, or even on rogue planets warmed internally, rather than by a star. The surface of such a world, viewed from space, would look like a cold, dead, reflective ball of ice. But below the silence, below the frozen crust, there might be warm, dark, liquid water. The kind of environment that on Earth shelters entire ecosystems at the bottom of the sea, far from any light, feeding on chemical energy from the rock below. Beneath a frozen surface, in the patient dark, the water stays warm and waits. The light from distant exoplanets takes so long to reach us that we are always seeing them as they were, never as they are. When we observe an exoplanet 100 light-years away, we are seeing light that left that system 100 years ago. The planet we see may have changed. Its atmosphere may have shifted. Its star may have brightened or dimmed. If there were beings on such a world looking back at us with comparable instruments, they would see Earth as it was 100 years ago, before most of the changes of the past century, before much of what has defined this era had yet occurred. We exchange images across time, not just across space. Every observation of an exoplanet is a postcard from the past, arriving in the quiet of the present. Every light that reaches us tonight left its source long ago. We are reading ancient postcards in the dark. Some exoplanet atmospheres show evidence of thermal inversions, regions where, counterintuitively, the temperature increases with altitude instead of decreasing. On Earth, the air grows colder as you rise through the troposphere, the layer closest to the surface. But in our stratosphere, ozone absorbs ultraviolet light, warming that higher layer and creating a thermal inversion. On exoplanets, particularly hot Jupiters, the substances responsible for thermal inversions appear to be metal oxides, titanium oxide, and vanadium oxide, absorbing radiation high in the atmosphere and heating that layer from above. This creates a situation where the high atmosphere is hotter than the layer below it, the sky growing warmer as you rise, not cooler. A world where the higher you go, the warmer the air becomes, until you cross the line and the cooling begins again. The sky grows warm above before it grows cold again, slowly, in the layers of a distant world. Tonight, while you breathe slowly, the universe is building planets. In the Orion Nebula, about 1,300 light-years away, there are protoplanetary disks surrounding young stars that are only 1,000,000 years old, barely infants by cosmic time. These disks have been imaged directly, glowing in infrared light, flat and rotating, perhaps 30 to 100 astronomical units across. Within them, the process of planet formation is actively underway. Dust grains collide, pebbles accumulate, planetesimals emerge. In 10 million years, there will be planets in those disks. In 100 million years, those planets may be solid and cooled and orbited by moons. They will be there, long after the sun has exhausted its fuel. New solar systems, born in the ancient light of the Orion Nebula, forming quietly while we sleep. In the Orion Nebula tonight, new worlds are forming in the slow and patient dark. An exoplanet's albedo, the fraction of starlight it reflects, determines how warm or cold it runs. A planet covered in bright white clouds or ice reflects a large fraction of the light that hits it, keeping it cooler. A planet covered in dark rock or ocean absorbs more, running warmer. Earth's albedo is about 30%. We reflect nearly a third of the sun's incoming light back into space. A planet with high albedo sits like a mirror in space, cool and bright. A planet with low albedo drinks in the light and grows warm. Albedo can shift over time as the surface changes, as ice melts, as cloud cover increases or decreases, as vegetation or dark rock is exposed. The brightness of a world is not fixed. It breathes with its own slow climate over thousands of years. A world's brightness is not fixed. It shifts slowly, breathing with its own long, quiet climate. Some exoplanets show evidence of active geological processes: volcanoes, plate tectonics, internal heat. On Earth, volcanism and tectonic activity play a crucial role in regulating climate over geological time, cycling carbon dioxide in and out of the atmosphere through what scientists call the carbon silicate cycle. A world with an active geological interior is one that can correct its own climate over millions of years, responding to warming or cooling by releasing or sequestering carbon. A geologically dead world, like Mars, loses this regulation and can drift into a permanent climate state from which it cannot return. Active geology is not just a feature of a living world. In some ways, it is a prerequisite for one. The planet must breathe to remain habitable. It must churn and crack and vent and seal, over and over, in the long dark. A living world breathes through its volcanoes, slowly, in a cycle older than any creature on it. The existence of exocomets, comets orbiting distant stars, has been confirmed through the faint, asymmetric dips they produce in starlight. Comets, unlike planets, have highly elongated orbits that bring them close to their star, heating them and causing them to shed gas and dust, exactly as the comets in our own solar system do. When an exocomet transits its star, the dust and gas tail, which trails behind the comet's nucleus, creates a distinctive lopsided pattern in the light curve. The drop in brightness is not symmetrical because the tail extends on one side. We have detected these signatures around dozens of stars. The same wandering, slow, dusty objects that pass through our own skies pass through theirs too, brushing the inner solar system briefly before retreating back to the cold dark of the outer reaches. The same wanderers that cross our sky cross theirs too, faint, slow, and briefly bright. The exoplanet K2-18b has been described as a Hycean world, a class of planet defined by a hydrogen-rich atmosphere over a global water ocean. The term is a portmanteau of hydrogen and ocean. Hycean worlds would be larger than Earth, warmer, covered in water, and wrapped in a thick atmosphere of hydrogen gas. If such worlds are real, they would represent a completely different kind of habitable environment, not Earth-like at all, but potentially capable of hosting microbial life in their oceans beneath the hydrogen sky. The hydrogen atmosphere would create a strong greenhouse effect, keeping temperatures elevated even at distances from the star, where an Earth-like world would freeze. Life, in this model, would not need Earth. It would need only water, warmth, and time. And the universe has provided all three in abundance. A world of warm ocean under a hydrogen sky, patient and ancient, not like ours, but possibly alive. You are still, and yet you are moving. As you lie here, your world carries you around the sun at roughly 67,000 miles per hour. The sun carries you around the center of the Milky Way at 500,000 miles per hour. The galaxy itself moves through space at more than 1,000,000 miles per hour relative to the cosmic microwave background, the faint afterglow of the Big Bang. And every exoplanet out there, every world in every distant system, is also moving, around its star, with its star, through the galaxy, through the vast structure of the local group, and the great web of galaxy clusters and filaments that makes up the observable universe. Nothing is still, everything turns. But from here, lying in the quiet, it all feels like stillness. Everything in the universe is moving, and yet in this moment, all you feel is still. Some exoplanets orbit in what is called the optimistic habitable zone, a slightly wider region around a star where, under certain conditions, liquid water might still exist, even though the planet would appear too hot or too cold by strict estimates. The conventional habitable zone is defined by models of an Earth-like planet with an Earth-like atmosphere. But if a planet has a thicker atmosphere, it can trap more heat and remain liquid water warm further from its star. If it has a different chemical composition, a different albedo, different cloud cover, all of these shift the effective range. The habitable zone is not a wall, it is a gradient, and what lies just outside it might be habitable under circumstances we have not yet fully imagined. The edge of the possible is softer than any boundary we have drawn. Life may live just beyond it. Biosignatures and exoplanet atmospheres are not just about finding life, they are about asking what life does to a world. Oxygen in our atmosphere is almost entirely the product of photosynthesis. Without living organisms producing it, the oxygen would quickly react with surface rocks and disappear. A world with oxygen in its atmosphere is a world that is actively resisting the natural chemistry of the universe. Similarly, methane and oxygen together in an atmosphere would be remarkable. The two react and destroy each other rapidly, so their simultaneous presence would suggest something is continuously producing both. We call this chemical disequilibrium, a state of the atmosphere that could not be maintained without a continuous input of something unusual. Life, from a distance, looks like a planet that refuses to be in equilibrium. Life looks, from a distance, like a world quietly refusing to behave the way chemistry expects. The planet GJ504b was one of the first exoplanets directly imaged, and it appeared distinctly pink in color, a pale, rosy magenta object against the dark of space. It is a young gas giant, still glowing from the heat of its formation. Not hot enough to shine brightly like a star, but warm enough to emit a faint pink-red glow in the infrared, detectable by our instruments. Over billions of years, it will cool. The pink will fade to a deep red, then to a dark rust, then to a cold invisibility. A world cooling slowly across millions of years, its color shifting with its temperature, going from warm and rosy to dark and cold, in a span of time that makes a human life seem like a single breath in a very long night. A pink world, cooling slowly over millions of years, its glow fading to the deep and patient dark. Some exoplanets in compact systems experience mutual transits, where from the surface of one planet, another planet in the same system can be seen passing visibly across the face of their shared star. In the TRAPPIST-1 system, with 7 planets in such tight orbits, this would be a relatively common occurrence. From the surface of TRAPPIST-1d, for example, the inner planets would appear as dark spots crossing the star's dim orange face on a fairly regular schedule, tiny circles of darkness moving slowly across the glow of the sun. To any observer standing on such a world and looking toward the star, the other planets would not be abstract points of light in the night sky. They would be visible, concrete, present, small dark shapes crossing the warm face of the star, slowly, in silence. Across the face of a shared sun, neighbor worlds pass slowly like shadows, visible and close. Some stars have lived so long that the planets around them have had time to evolve through geological ages we cannot fully comprehend. The oldest stars in the Milky Way are nearly 13 billion years old, almost as old as the universe itself. If any of those stars host rocky planets, those worlds have had 13 billion years of geological time, 13 billion years of cooling, of volcanic cycling, of atmosphere building and stripping and rebuilding. Earth, at 4.5 billion years old, is a relatively young world. A planet around one of these ancient stars would be nearly 3 times our age. Whatever processes shaped it began so long ago that the early universe was still crowded with young, bright stars when they started. We are newcomers to a neighborhood that has been inhabited, in some form, for an almost unimaginable span of time. We are young here. The universe has been doing this, quietly, for far longer than we arrived. The chemical composition of a star directly determines what kinds of planets can form around it. Stars with higher ratios of carbon to oxygen produce planets richer in carbon compounds, potentially diamond-cored worlds, graphite crusts, and carbide minerals. Stars richer in magnesium and silicon produce worlds more like Earth. Silicate rock, iron cores, the familiar mineralogy of a terrestrial world. We are, in a very direct sense, made of our star. The iron in the ground beneath you came from the same cloud of gas and dust that formed the sun. The silicon in the rock under every ocean was cooked in the same ancient stellar generations that produced the raw material for our solar system. The chemistry of a world is the chemistry of its star, translated into stone. We are the translated chemistry of an ancient star, resting in the form the universe gave us. There are exoplanets in systems so metal-poor that their rocky worlds may have no iron cores at all. In astronomy, the word metal refers to any element heavier than hydrogen and helium: iron, silicon, carbon, oxygen. The first generation of stars, formed just after the Big Bang, was almost entirely hydrogen and helium. They had no metals at all. The metals were created in those stars and spread into the universe when they died. Planets forming around the earliest, most metal-poor stars would have had very little iron or silicon to work with. They might be composed almost entirely of exotic materials we do not have in our own solar system. Strange, ancient worlds made of the universe's first chemistry, predating everything that came after. The oldest worlds may be made of things we have no word for, built from a chemistry the universe has since moved beyond. Tidal heating can make a world geologically active even with no star nearby. When a moon or planet is caught in the gravitational tug-of-war between a large planet and other moons, the constant flexing of its interior generates heat. On Jupiter's moon Io, this process drives the most active volcanism in the solar system. On a large exomoon orbiting a giant planet, the same mechanism could maintain liquid water beneath a frozen surface, even far from any star. The heat does not come from above, from light. It comes from within, from the squeezing and releasing of the rock itself. Billions of tons of planetary material, bending and flexing imperceptibly with each orbit. A world warmed not by a sun, but by the slow, rhythmic kneading of gravity. Warmth rises from the deep, not from a star above. The world warmed gently from within, by the rhythm of its own orbit. When a planet is large enough and hot enough, it can emit detectable infrared radiation from its own interior heat. Young gas giants, formed only tens of millions of years ago, still carry the thermal energy of their formation, the heat released when billions of pieces of material collapse together under gravity. This process is called accretion heating, and it gradually leaks away into space over billions of years. By detecting the infrared glow of such a planet against the background of space, we can infer its temperature, its age, and something about its interior. A young gas giant, seen in infrared, glows dimly, not the fierce light of a star, but a faint, warm presence in the dark, like an ember that has been cooling for 50 million years and has not yet gone fully cold. A world still cooling from its own birth, glowing faintly in the dark, with a warmth no longer new. The inner edge of a habitable zone is defined by a process called the runaway greenhouse effect. If a planet receives too much stellar energy, water begins to evaporate from the surface. Water vapor is itself a powerful greenhouse gas, so as it builds up in the atmosphere, it traps even more heat, causing more evaporation, causing even more warming. A feedback loop with no natural stopping point. The entire ocean evaporates. The water vapor eventually reaches the upper atmosphere, where it is broken apart by ultraviolet radiation, and the hydrogen escapes to space. The planet loses its water permanently. This is believed to be what happened to Venus, a world that may once have had oceans, that crossed the inner edge of the habitable zone as the sun gradually brightened over billions of years and quietly boiled away everything that might have made it otherwise. A world that once had water crossed an invisible line and slowly lost the thing that kept it possible. Astronomers use the term photometric precision to describe how accurately a telescope can measure the brightness of a star, And the extraordinary precision required to find Earth-like planets around Sun-like stars is humbling to consider. Finding an Earth around a Sun requires detecting a dimming of 1 part in 10,000, a brightness change equivalent to the shadow of a mosquito crossing a car headlight from a mile away. The fact that we have built instruments capable of this from Earth orbit is a quiet monument to the patience and precision of human science. Not loud science, not fast science, but the careful, incremental kind that builds instruments over decades and stares at the sky for years, waiting for the faintest possible signal to arrive. Quietly, patiently, over decades, we built instruments sensitive enough to feel the shadow of a mosquito a mile away. Some exoplanets are caught in what is called a mean motion resonance, where the gravitational interactions between neighboring planets cause them to exchange small amounts of orbital energy at regular, predictable intervals. Over billions of years, this resonance acts like a set of invisible rails, keeping the planets in stable lanes and preventing the kind of orbital chaos that might otherwise eject one of them from the system entirely. It is a form of gravitational communication. The planets do not touch, do not see each other, cannot feel each other in any sensory way. They feel only gravity, and through gravity, they negotiate, adjust, accommodate, and stabilize on timescales that make human negotiation look like a single whispered word in an infinite conversation. Two worlds negotiate their paths in silence, through gravity alone, across millions of years. Some exoplanets may have formed not in a protoplanetary disk, but by direct gravitational collapse, a process more like how stars form than how planets typically do. In the core accretion model, planets build up grain by grain over millions of years. In gravitational instability, a region of the protoplanetary disk becomes massive enough that it collapses under its own gravity all at once, forming a giant planet in perhaps a few thousand years, a geologic instant. Some of the very large, very widely separated gas giants we have directly imaged may have formed this way. They are planets by size, but the process that made them was more like the process that makes stars. They sit at the edge of two categories, quietly occupying a space the universe did not restrict. A world formed like a star, but never became one, patient, at the boundary between two kinds of things. Even now, as you drift, every rocky exoplanet that has ever formed has carried the seeds of complexity from its very first moment. The same basic chemistry, carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, is distributed throughout the galaxy, assembled from the remnants of dead stars. These are the 6 elements most essential for life as we know it, and they are not rare. They are among the most common products of stellar nucleosynthesis. If they can combine into self-replicating molecules on Earth, the conditions for that to happen elsewhere are not extraordinary. The universe did not build life in a special place with special ingredients. It scattered the ingredients everywhere, in nearly equal measure, and waited to see what they would do. The ingredients were everywhere from the beginning. The universe scattered them and waited, quietly, for something to happen. Some exoplanets have been caught in the process of migrating, moving slowly inward toward their star over millions of years, dragged by interactions with the gas and dust of the protoplanetary disk. This process, called Type 1 or Type 2 migration, depending on the planet's mass, is how hot Jupiters are thought to have ended up so close to their stars. The planet does not move fast. It does not leap. It slides, a millimeter here, a kilometer there, over millions of years, drawn toward the center of its solar system by the friction of the disk material. Most of this migration stops when the disk dissipates. Some planets spiral all the way in and are consumed. Others park at a stable inner resonance, and some reach a point where nothing is pushing them anymore and simply stay, wherever they ended up, which is not where they began. A world that wandered inward over millions of years and stopped, simply where the pushing ended. The starlight falling on a distant exoplanet began its journey at the surface of that planet's sun, generated by nuclear fusion in the star's core, taking perhaps 100,000 years to work its way through the radiative zone, and then another 8 minutes, or 8 hours, to cross the space between star and planet. The same light that warms the surface of an exoplanet, that drives whatever weather exists there, that illuminates whatever landscape stretches away in every direction, was born in a star and traveled to that world in a quiet, continuous flow. Light is not instantaneous, it is a journey. And the light reaching any world at any moment is light that has been traveling for a specific, calculable period of time. Every world is bathed in the past. Every world is lit by the past, by light that left its source before it arrived at anything. The surface of a planet and the bottom of its atmosphere are not the same boundary. On Earth, the atmosphere extends from the surface up to the edge of space, gradually thinning, layer by layer, until there is no meaningful distinction between air and vacuum. On a gas giant exoplanet, there may be no solid surface at all, just a gradual transition from low-density gas at the top to higher-density gas lower down, and eventually to metallic hydrogen or a liquid core deep within. The concept of a surface, somewhere to stand, somewhere for things to fall, does not apply. If you descended into such a planet, you would not hit the ground. You would just feel the air grow thicker and heavier and hotter, pressing in from every direction as you went deeper, until the pressure became something no solid object could survive. There is no ground at the center of a gas world, only the deepening dark of endless air pressing inward. Exoplanet science is still young. The first confirmed planet around a sun-like star was found in 1995, barely 30 years ago. In that time, we have gone from 0 confirmed exoplanets to more than 5,000, with thousands more candidates. We have developed new detection methods, launched dedicated space telescopes, and begun reading the chemical composition of other worlds' atmospheres. And we are still at the very beginning. The James Webb Space Telescope is the most powerful instrument we have ever pointed at the sky, and it is just now producing its first detailed atmospheric studies. What the next generation of telescopes will find, the extremely large telescope in Chile, the Habitable Worlds Observatory being planned for the 2040s, we cannot yet say. We are, as always, at the beginning of what we know. We are always at the beginning. The universe is always older than we thought it was. There are places in the galaxy where planets cannot form at all, regions near the galactic center, where stellar density and radiation are so extreme that protoplanetary disks are destroyed before they can produce planets. There are regions in the halo of the galaxy, far above and below the plane, where the elemental composition of the gas clouds is so metal-poor that only small, exotic, primitive worlds could ever form. There are globular clusters, ancient collections of hundreds of thousands of stars, where the stars are packed so close together that planetary orbits would be gravitationally disrupted before they had a chance to settle. The galaxy does not distribute its hospitality evenly. Some regions are generous, others are ancient and bare, and not built for worlds like ours. The galaxy holds its hospitality unevenly. Some corners are ancient and quiet and bare. As you rest tonight, consider that the light leaving our sun right now will reach the nearest stars in about 4 years. Some of it will continue past them, past the Oort cloud, past the heliopause, past the faint outer edge of our solar system's influence, and drift through interstellar space for millions of years before encountering anything else. Tiny packets of energy, released from the surface of our star, carrying information about the sun's temperature, its spectrum, its size, drifting away into the dark at the speed of light, alone, in every direction at once. One of those photons, heading in exactly the right direction, will eventually reach the star that hosts Kepler 452b in about 1400 years. Our sun's light is already on its way to 1,000 other worlds. It left without asking. It will arrive long after we are gone. Our sun is already sending light to other worlds. It left without ceremony. in every direction at once. The diversity of exoplanet systems is so extreme that every general rule about planets has exceptions. Most planets orbit in the same direction as their star's rotation, but some orbit retrograde, backward against the spin of their sun. Most planets orbit in roughly the same plane, but some orbit in highly inclined paths, nearly perpendicular to the equator of their star. Most planets in a system have roughly similar sizes, but some systems contain planets ranging from less than Earth mass to many times Jupiter mass in the same compact arrangement. The universe does not follow our rules for how solar systems should be built. It runs every experiment, in every configuration, without preference or agenda, and then it waits, quietly, to see which experiments last. The universe runs every experiment without preference, then waits quietly to see which ones hold together. Exoplanet atmospheres can be studied even without the planet directly transiting its star, using a technique called eclipse mapping. When the planet passes behind its star, disappearing from view, the total light of the system briefly decreases by a tiny amount. By comparing the light just before and after the disappearance, scientists can subtract the planet's contribution and learn about its brightness and temperature distribution. As the planet rotates in its orbit, different parts of its day side come in and out of view, allowing astronomers to build a rough map of temperature across the surface. A map drawn from light curves alone, never seeing the surface directly, inferring the landscape from the way it shines. Science, as a form of patient reading, decoding a world from the shadow it leaves in the light. A world mapped by its shadow, never seen directly, decoded from the faint language of light and dark. Some exoplanets have been found to have extremely high eccentricities, elongated orbits, that swing them from scorching proximity to their star to the distant cold of the outer system in a single year. A planet with an eccentricity of 0.9, which some known exoplanets approach, would spend most of its year in the cold, far reaches of its orbit, then plunge inward on a fast, tight arc, briefly sweeping close to its star before being flung back outward. The change in received starlight between the farthest and closest point in such an orbit can be a factor of 100 or more. Any atmosphere on such a world would undergo extreme seasonal cycling, freezing in the long, cold dark of the far arc, thawing rapidly as the planet swings inward, then freezing again as it retreats. A year like a deep breath, fire and ice on the exhale and the inhale. A year that moves from ice to fire and back again, breathing in cycles too long for any living thing to witness in full. Some rocky exoplanets in tight orbits may have surfaces perpetually reshaped by a global magma ocean. If the tidal forces from a nearby star are strong enough, and if the planet receives enough radiation, the surface may never solidify. It would remain molten, a global ocean of liquid rock, slowly churning, thin crust forming at the surface and sinking back down before it can harden. Volcanic activity would not be localized, as it is on Earth. The entire surface would be volcanic. It is hard to picture because nothing in our experience resembles it. Not the hottest lava flow, not the biggest eruption. Just a world made entirely of liquid stone, quietly glowing, circling its star in a state of permanent, gentle catastrophe, never cooling enough to settle. A world of liquid stone, glowing faintly, too close to its star to ever cool and be still. The planet HD 40307 grams was once considered one of the more promising super-Earth candidates in the habitable zone of its star. It orbits at a distance where temperatures might allow liquid water, and it is large enough that it could maintain a substantial atmosphere. It was found using the radial velocity method, and its existence was confirmed after careful analysis of the stellar wobble data. What is quieting about HD 4307 grams is not what we know about it, it is how little. We know its orbital period. We know approximately how massive it is. We know its star's type and brightness. Beyond that, almost nothing. Whether it has an atmosphere, whether it has water, whether it has any surface to speak of, all of this remains unknown. a world confirmed to exist and almost entirely mysterious. A world we have confirmed and named, and about which we know almost nothing. Quietly, that is enough for now. There are stars in the Milky Way so old that if they formed planets, those planets have had time to experience the rise and fall of civilizations. If civilizations can exist, billions of times over. A planet around a 12-billion-year-old star would have had more than 2.5 times Earth's entire history in which to develop, evolve, change, and change again. Whatever life may have arisen on such a world, whatever intelligence, whatever culture, whatever accumulated knowledge, it would have had timescales we cannot reason about. If any such civilization arose and then declined, the evidence of it may be long gone, dissolved into geology, scattered by erosion and volcanism, pressed into unrecognizable mineral form. We would never know. The universe is old enough to have forgotten things we have not yet thought to ask about. The universe is old enough to have held and lost things we will never know to look for. And in the end, what is an exoplanet? It is a world, a round thing, moving around a star, following the laws of gravity and thermodynamics and orbital mechanics, in the same way our world does, in the same way every world in this galaxy does. It carries its own geology, its own chemistry, its own relationship with the light of its sun. It does not know it exists. It does not know we have found it, named it, measured its orbit, guessed at its atmosphere, wondered about its surface. It simply turns, patient and ancient, in the dark between stars. And we, from our small blue vantage point on the edge of one quiet spiral arm, have learned to find these worlds one by the faint shadow they cast, by the tiny wobble they cause, by the light they absorb or reflect, or gently redirect as they pass. Every world turns in the dark, not knowing it is known. We found them anyway, quietly, one by one. Some exoplanets are so far from their stars that their surfaces receive barely more heat than the background radiation of the universe itself. The cosmic microwave background, the afterglow of the Big Bang, permeates all of space at a temperature of about 2.7 degrees above absolute zero. A planet far enough from its star that starlight contributes almost nothing to its thermal budget would be warmed, barely, by the faint warmth of the Big Bang itself, the oldest warmth in the universe. The residual heat of creation, still traveling, still touching everything, still arriving at every surface, in every corner of space, 14 billion years after it was born. A cold world, barely warm, bathed in the most ancient light there is. The oldest warmth in the universe still reaches every cold and distant world, faintly, across 14 billion years. Quietly, the cosmos moves around you. You are lying on a world that is itself an exoplanet from the perspective of any being in another solar system. The same methods we use to find distant worlds, the transit, the wobble, the spectrum of light, could be used, in principle, to find us. Our sun wobbles because of Jupiter. Earth creates a dimming of 1 part in 10,000 as it transits the sun, visible from exactly the right vantage point in space. Our atmosphere has oxygen, water vapor, carbon dioxide, a chemical fingerprint that no purely geological world would have. We are detectable, in theory, from dozens or hundreds of light years away. We are, to someone with the right instruments and the patience to look, an exoplanet, a blue signal in the dark. We are the exoplanet someone else has not yet found, a blue signal drifting quietly in the dark. Far out in the Milky Way, beyond the reach of our current instruments, there are worlds we will never see, not because they do not exist, they almost certainly do, but because the light from their transits is too faint, their stars too small, the distances too vast for any telescope we will build in any human lifetime. They turn in silence, undetected, in the deep outer arms of the galaxy and in the spaces between the spiral structures. They are real. They follow the same physics. They were made of the same stellar generations. and they will never be named. They will never be measured. They will never be in any catalog. They exist in the same universe we do, turning quietly in the same dark, and we will simply never know they are there. Somewhere, a world turns in the dark that we will never find, unnamed, unknown, and just as real as this one. Some things in the universe are too vast for any single mind to hold, and the number of worlds in the observable universe is one of them. Estimates suggest there are at least 100 billion trillion stars in the observable universe, a 1 followed by 23 zeros. If even a fraction of those stars host planets, the number of worlds is effectively beyond counting, beyond any number with a name, beyond any metaphor that fits inside a human mind. And each of those worlds is as complex as this one. Each has its own orbit, its own chemistry, its own geological history, its own relationship with its star. Each one is a complete thing, a full thing, a world. There is no word in any language for a number that large. There is only the quiet that comes after you try to imagine it and give up, gently. Some numbers are too large to hold. We let them go and rest in the quiet that follows. Even now, as you drift, the universe continues its patient work. Stars condensing from cold gas clouds, planets accreting from swirling disks, moons forming from the debris of early collisions, comets sailing their long elliptical paths. None of it pauses for anything. The formation of worlds does not stop when civilizations rise or fall. The spiral arms of galaxies continue to rotate. The universe expands, gently, at every point, the space between galaxies growing wider with each passing second. All of this is happening right now, as you breathe, as your eyes grow heavy, as the thoughts of the day dissolve, and the body surrenders to sleep. It does not require your attention. It simply continues, as it always has, patient and vast, and completely indifferent to whether anyone is watching. The universe continues, whether or not anyone is awake to see it turning. The stars above you tonight are the same stars that hung above every sleeping thing that has ever lived on this planet. Every creature that has ever closed its eyes and drifted off, every animal that has ever found a warm place and stilled itself, has done so beneath the same slow wheel of stars. The constellations shift over thousands of years as the Earth wobbles on its axis, but the stars themselves persist. Orion's stars were there before the first human named them. They will be there long after the last eye closes on this world. Tonight, they are above you, very far away, very old, very quiet, burning steadily, as they always have, in the dark above every sleeping world. The stars were above every sleeping thing that ever lived, and tonight they are above you too. The nearest exoplanets are so far away that even the fastest object humanity has ever launched would take thousands of years to reach them. Voyager 1, traveling at about 38,000 miles per hour, would take roughly 70,000 years to reach the nearest star, and that star has no confirmed planet. To reach Proxima Centauri b, our nearest known exoplanet neighbor, at the same speed, would take a similar span. The world you are lying on right now is isolated in a way that is difficult to fully feel. Space is not empty, it is full of worlds, but the distances between them are so immense that they amount to a kind of profound, gentle solitude. We are here, warm and breathing, on this particular world, in this particular solar system, at this particular moment in the universe's long history. We are here, in this moment, on this world, and the distance to everything else is its own kind of peace. There is something calming in the thought that right now, as you lie still, as your breathing slows, a planet somewhere is completing an orbit it has completed billions of times before. Not thinking about it, not aware of it, just moving, as it always moves, in the path it has always followed, around the star it has always circled. Patient beyond any patience a person can feel. Ancient beyond any age a mind can hold. Not in a hurry, not uncertain, just turning and turning in the dark. A world turning in the dark, as it has always done, not knowing it is beautiful. The light from a star reaches its planet in minutes. The knowledge of that star takes years to reach us, and the understanding of what that knowledge means takes lifetimes. We are always catching up. The universe is always already further than we have reached, and somehow, that is not discouraging. It is restful. There will always be more to learn. The questions will not run out. The sky will not be exhausted. There will always be another world to find, another signal to read, another spectrum to decode. The darkness between the stars is not empty. It is full of things that are waiting, quietly, for the right instrument to look in exactly the right place, at exactly the right time. The dark is full of things still waiting to be found, and we have all the time in the universe to look. A single breath, taken now, slowly, in the dark of a quiet room. That breath contains atoms that have traveled through stars. The oxygen in your lungs was forged inside a star that died before our sun was born. And the carbon in your cells has been part of cosmic clouds, planetary surfaces, ancient seas, and the bodies of 1,000 other organisms before it came to rest in you. You are not separate from the cosmos you have been reading about tonight. You are part of it, made of it, assembled from the same material as those distant worlds, by the same processes, on the same timescales, in the same universe. The exoplanets we have been talking about tonight are not somewhere else. They are part of the same story you are part of. You are not looking at the universe from outside. You are the universe, resting and breathing, looking quietly inward. And here, now, is where we slow all the way down. The iron in your blood was forged in the heart of a dying star, not as a metaphor, not as poetry, as fact. The iron atoms that carry oxygen through your veins right now were synthesized in the core of a massive star billions of years ago, in a supernova explosion that scattered those atoms across light years of space. They drifted in a cold molecular cloud. They collapsed with that cloud when it contracted under gravity to form our solar system. They accreted into the rocky planet you are resting on. They dissolved into the early ocean. They were drawn into living cells. They have been moving through living things on this world for hundreds of millions of years. And tonight, they are in you, doing the quiet, ancient work of keeping you alive. You are held together, in part, by the work of a star that died before the Earth existed. The cosmos did not make you separately from itself and then place you inside it. It made you from itself. Every atom in your body has a history that begins in a star. And your hydrogen is as old as the universe, formed in the first 3 minutes after the Big Bang. Your oxygen came from a red giant, your carbon from another, your calcium, your phosphorus, your nitrogen, each with their own stellar biography, each with a journey of billions of years before they arrived, in the particular arrangement that is you. You are not a visitor to the cosmos. You are a thing the cosmos made, temporarily, from the best materials it had. Let your breath slow now. Let the weight of your body rest fully against whatever is beneath you. You do not have to hold anything up. The universe does not need your attention tonight. It knows what it is doing. It has been doing it for 14 billion years without pause, without hurry, without any need for any of us to be awake. The exoplanets are still turning. The stars are still burning. The space between them is still vast and dark and quiet. And you, made of the same ancient material as all of it, you are allowed to rest. There is nothing left to figure out tonight. There is no place you need to be. You are here, on this small, warm world, under these stars, and everything is as it should be. The galaxy will continue its slow rotation. The nearest exoplanet will complete another orbit. The light from 1,000 distant suns will continue crossing the dark, and you will sleep, softly and well and deeply, the way the universe rests between the stars. I hope you sleep well tonight.